Okay, this video is going to be about cross sections. I'm going to put in squares, equilateral triangles, and semicircles. And again, those are the shapes that are going to be the cross sections. And what we're going to do here is we're going to line this region. And what you're looking at right now is the XY plane, right? The red is the x-axis, the green is the y-axis. This is the curve x squared, and this is the curve square root of x. And we're going to fill this shape here, right, below the red and above the blue, this kind of like teardrop shape. We're going to fill it with different cross-sectional shapes. Okay, so we're going to put squares in there, we're going to put equilateral triangles in there, we're going to put semicircles in there. Each one of the shapes are going to have a thickness or width of dx, and then they're going to have different cross-sectional areas, which will then form different 3D shapes. Again, we're looking at the three-dimensional volume of a shape formed by putting in squares or rectangles. Okay, so we're going to, let's do, I don't know, 10. Okay, so this is using 10 different squares. Each square, so a square, all of these are squares, and from above, well, of course, they just look like a line. And if I rotate this thing, then I'm going to be able to show you in a different view of a plane that they're actually squares. Again, if we look at this now, we can see that those are the heights of the squares, and then those are visually the square. As you can see, we take a line, go choom, 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 all the way across. The thickness of each square is dx. The area of each square, well, of course, that's just this distance. And again, what is that distance? Well, if you take the top curve minus the bottom curve, right, in this case, it'd be the square root of x minus x squared. That's this purple distance that you're looking at here. And again, it just looks like a line in 2D when you're looking straight at that plane. But then we can find the area of the square. And the area of the square times the thickness of the square gives you the volume of the rectangular prism, and then you sum up all those things. So this is what it'd look like if you filled this region with 10. There's 20 squares. Hopefully you can see. I'm just getting a better view of that volume. Again, from this perspective, they just look like straight up and down. If I tilt it this way, you can kind of see then the squares. And then if I fill it with a whole bunch, that would be 100. Well, then it just looks like the three-dimensional shape that it actually is. Again, kind of got that idea. If I scale it down, I can see the squares easier. Lower, lower, and lower, and all of a sudden I can see the squares. Again, instead of squares, what if I put in semicircles? Again, from this point of view, you can't tell what I'm putting in, whether I'm putting in semicircles or squares. In this case, if I put a semicircle in between here, and again, this would be an n of 12, these are 12 of them. This is the diameter of the semicircle. Tilt it to the side, and then you can actually see the circles. The circles are the cross-sectional areas. Well, how would you find the volume? Well, the volume in this case would be integrating from 0 to 1 of 1/2 pi r squared. Again, 1/2 because they're semicircles, and r, well, because that's how you find the area of a circle, right? 1/2 pi r squared for semicircles, and r would just be half of this length. Again, this length is the diameter of the circle, so just find that length, divide it by 2, and then you can find the radius, and those are the circles. And again, I can increase it to, there's more circles, and again, you can see all those circles from up top. It will just look like that. We're just filling in the gaps from the side. You can actually see the cross-sectional circles, and then if I make it, 100 of them, then you have a very similar shape, except here, those are actually semicircles. That's a nice curved space there instead of being squares. And again, I can change it from semicircles to squares, and from that point of view, you can't even tell a difference. They're squares, they're circles. Okay, here, and again, if there's too many of them, you can't tell what they are either. I'm going to tone it down back to like 20. There's filling it with semicircles, there's filling it with squares, there's filling it with equilateral triangles. Again, from this point of view, it's the exact same look. They just look like lines. You tilt it to the side, and then you can actually see the cross-sectional shape. Again, we can tone that down. Right, we're filling this gap with triangles. The triangle's base lie in the plane xy, in between the curve, square root of x and x squared. The thickness of them are just dx. They look like this. You tilt them aside and you can actually see the cross-sectional area. So these really aren't triangles, they're really triangular prisms. The prisms have thickness dx, area, if they're equilateral triangles in that particular case, and again I'll show you in the next part, is square root of 3 over 4 L squared, where L is this distance. And you just put in more and more triangles, and all of a sudden you get a perfect view of what the three-dimensional shape would actually be. Again, the 3D shape on this side is nice and flat. All the triangles lie in the plane. They're all lying in that plane. So looking at the bottom, it's nice and flat. And the top, they're going to go up. And how high they're going to go up? Well, they're going to go up just as high based on this curve. Again, it's an equilateral triangle situation. Okay? So those are the most three popular, and those are easy. We can put in other shapes. We can put in rectangles. We can actually put in circles, in which instead of being flat at the bottom, instead of being flat like semicircles, it would be symmetrical on the top, but then the bottom would look identical. Okay? I'm not going to do a video showing if we put the circles the other direction, but again, it's the exact same thing. Everything is just, instead of dx, it's just dy, and it's this distance. Okay, hopefully that gives you a good start on cross-sectional areas. The next part of the video will actually go through the math of how you'd really set it up given those two curves. Okay, let's continue to talk about finding the volume using cross-sections. And again, what we mean by cross-sections is that we're taking some sort of space in the xy plane. Let's look at the space in between the curves y equals x squared and y equals the square root of x, right? Y equals x squared is this quadratic here that's on the bottom, and then the square root of x kind of curves over like this, and they do meet the point 1, 1. So this red area here is in the plane, in the xy plane, and we're going to fill it with certain shapes. And again, the video does a much better job of actually drawing this, but right here, this is just the base of the shape. And so if we put squares in there, again, each one of these things end up being a square. So there's a square here, a square here, a square here. We're going to line this thing with squares, okay? Because all of these rely on this same principle, as we showed in the video. The volume of the three-dimensional shape is summing up the volume of each individual shape. Each individual shape has a cross-sectional area times the width, right? This dx, that's just the width. Here, that's the thickness. And then again, you can't see it looking down on it. You have to look from the side here in a different dimension to actually see the square. But this right here, this bold thing, is really just a square. And so the square looks like this. And how do you find the area of the square? Well, you just take L squared. Well, what is L? Well, L is this length. This length is the top curve minus the bottom curve. So how do you find the volume with this square? Well, then the volume is you're going to sum up the area of each square. Each square is the square root of x minus x squared squared. That's the area of the cross-sectional shape dx, and we want to sum them up from 0 to 1. Okay, sum up all the squares area times the thickness. Remember, the thickness is the width of this little bitty blue thing right here, which is dx, right? That little thickness right there is dx. And then the cross-sectional area, I'm looking at it from a different angle. Again, the video does a much better job of actually showing you the square. Well, it's just L squared, and L is this distance. This distance is just top curve minus bottom curve, right? The difference between this y value and this y value gives you that length. Okay, well, what about semicircles? Well, a semicircle is kind of going to look like this, right? And how do you find the volume? Excuse me, the area of a semicircle? Well, it's 1/2 pi r squared. So then, how do we find the volume? Well, we always do the same thing. We're just adding up all these things from 0 to 1. Okay, here, if it's a semicircle, we're looking at that as our cross-sectional area. So that's 1/2 pi. And then r. Okay, this is where it gets a little tricky. R for a circle is half the diameter. This distance is the diameter of the semicircle. So what we really need to do is take the square root of x minus x squared and divide it by 2. All of that divided by 2 is actually the radius. And then if we take 1/2 pi r squared, that's the cross section of the semicircle, give it some thickness dx, and then that's the volume of those semicircles in 3D, and then we need to sum them up. Again, this distance L is the top curve minus the bottom curve, but this is the diameter of our semicircle, which would all come out of the shape like that. Okay, so we have to divide that by 2. If we just wanted circles, well then what we're doing is the diameter of the circle lies in the plane, and then it would come 3-dimensionally up, but then it would also just come down. And so all of these are nice and flat. This one, if you filled this with circles where the diameter lies in the plane, well, this would come up and it would go down. And it's really just as easy as taking away that half. Summing up circles is just summing up pi r squared. R is still that distance, which is the diameter divided by 2 squared dx. Okay? All right, a rectangle. So let's slap in a rectangle here. So there's one side of the rectangle, and let's say the other side. And so they'd have to tell you the dimensions of the rectangles they want to put in. So what if they said something like, let's make the rectangles 3 times as high as they are wide? Well, what's the area then? Well, it's like saying they want this to be some L, and they want this to be 3L. So the distance that's going to come off the page is 3 times this particular distance. And again, the volume is the same. We're going to sum up all these really, really small rectangular prisms, right? The cross sections are rectangles, and their widths are dx. So they're really rectangular prisms. So L, well, we're going to sum from 0 to 1. We're still going to sum up L because the area of this rectangle, well, that's just L, square root of x minus x squared, times 3 times the square root of x minus x squared. That's L times 3L, and that's the cross-sectional area of this guy times its own thickness. Okay? So that one's a little tricky, but it just seems, I mean, it's very similar to the square, except this dimension is just 3 times longer, so instead of this times itself, it's this times 3 times itself. Okay, so hopefully you can imagine that this is just going to be 3 times the volume of this. Hopefully that makes sense because this 3 can just factor out. Okay, and then the trickiest one is, hey, they want to put in equilateral triangles. And again, the video hopefully did a good enough job of showing you what that would look like. But we're still taking this same shape. And in here, we're putting in equilateral triangles. So the triangles all have bases like this, but then they go up. And we're stacking all those triangles in there. Okay, well, how do you find the area of an equilateral triangle if you know the side length? Whew, that takes a little work. So let's do that real quick. If you know that this is L, then you know this is L and you know this is L. So what's the area of this guy if you only know L? Well, it turns out, let's drop a vertical. This we know is 60 degrees. We know this is L over 2. Besides the fact that it's a 30, 60, 90 triangle, I mean, they split this base into half. So this distance is L over 2. But we also know what the height is. So the height of this triangle is the square root of 3 times h over 2. And I'm just using the fact that I know a 30, 60 triangle. Right? We know a 30, 60, 90 triangle is 1 square root of 3, 2. If this is 60 degrees and this is 30 degrees. So I'm taking this side length, the square root of 3 times this side length, so that I know that. Okay? So then the area of this guy, the area of any triangle is 1/2 times the total, times the base, right? I'm looking at the big blue triangle, the base is L, times the height. Oops, my bad, that H, that was silly. That was an L. Times the square root of 3 over 2L. And it turns out then the area of an equilateral triangle is 1/4, or the square root of 3 over 4 L squared. Okay, and that's a formula, and I derived it. You could just memorize it. So then if I want to find the volume of this bad boy, the volume of stacking equilateral triangles in this plane, again, we're stacking a triangle and a whole bunch of them, we're still going to integrate from 0 to 1 of the area. And the area of an equilateral triangle is the square root of 3 over 4 L squared. L, well, that's this distance still, square root of x minus x squared, and then give each of them thicknesses and add up all those 3D triangles, right? They're kind of like triangular prisms. Add them all up and then get the volume. Okay, those are the 5 most popular types of cross sections. I can change these curves to whatever I want. It's not going to matter. As long as I can find this distance, L, in my diagrams, then I can do squares and rectangles. I can cut L in half to find the radius for semicircles and circles, and then equilateral triangles, I kind of derive the formula for the area of an equilateral triangle if you know the side length. And if you're putting equilateral triangles in this space, then this distance is the side length, which is equal to all the side lengths, hence equilateral. Okay, so hopefully this gives you a good start. The video at the beginning kind of gave you the visual, and this kind of went through the actual calculus.